Swayam Prabha. Digital India. Educated India.
Hello everybody, we are discussing the topics in the course High Performance Computing for Scientists and Engineers. We are in the third module and 20th lecture of this course, which is Introduction to MPI and Distributed Memory Parallel Programming. We are basically continuing from last lecture. So in the last lecture we have discussed about shared and distributed memory computing and tried to get some comparisons in between them and identified the important features of distributed memory computing, because while doing MPI we are basically working on distributed memory parallel programming. So we will start with comparing distributed and shared memory programs, at least algorithm wise. One of the examples which we have worked also on while learning OpenMP and shared memory programming is numerical integration, that we have to integrate a function between certain values 0 to 1 or x1 to x2. Here we distribute, we do a numerical integration that we distribute into many small finite many small finite trapezoids and try to find out the area of the trapezoid and sum it up. So if we try to get a very accurate estimation of the integration, the number n over the intervals over which we are summing it up, the function multiplied by delta x, distance between the intervals up or width of the interval, this number must be very high. The number n, if we try to get accurate estimation of the integration, the n must be a large number. So as it is a large number, there will be, if we try to write a simple C program, we have seen that there will be many number of iterations. So we try to ask multiple processors to take care of that. Each processor will execute part of the integration and finally they will sum up the value. So what will like that, there will be say there are 4 processors, each is trying to do the integration for certain for the portion given to it, for certain amount of steps given to it, and they are doing it concurrently. So finally everything will be summed up. So in a shared memory machine, we can see that a shared memory program, we can see that there are 4 threads, each processor is running 1 thread here, and each one is finding the local sum I0, I1, I2, I3, and these local sums I mean after after each thread has finished their work, there is a barrier and only thread 0 is active. After the barrier, all the threads are destroyed. But however, the value I1, I2, I3, I0 being shared memory variable, they are available to the main RAM. So thread 0 gets all these values and sums them up and finds I. And we have seen that there are, while writing these sums, there can be false sharing issues, we have to use padding or critical construct, etc. But this is the basic model, that each processor computes the local sum, stores in a shared memory array, and after the parallel part, the final summation must be done sequentially. So there is a barrier where all the threads are destroyed and only the thread 0 is active, who reads all these variables from the shared memory and sums them. What happens in distributed memory? In distributed memory, the memory units are distinct. So each processor finds its own local sum. Processor 0 finds its own local sum I local, it names it I0 for certain purpose, we can see that. Processor 1 finds the local sum which is again I local, because there is no meaning of writing I1, I2, I3. Each processor, the processor has its local sum which is not being seen by the other processors. So how to find out the summation? That after this part, when the final sum has to be found out, other processors have no work, because this is one sequential step. So processor 0 retains the local sum as I0 and other processor sends the value, their local value, to processor 0 as I1, I2, I3. So this is the data transfer part where I local of processor 0, I local of processor 0 is copied as I1 here. I local, the local integration of processor 2 is copied as I2 here. The local integration of processor 3 is copied as I3 here. This is the data transfer step. So these processors have their own remote local data. They send this information that this is the value calculated by them through network cable to the 0th processor, and now 0th processor sums up and gets the final integration. So that is the main difference, that here they do not need to send anything because everything was being written to the same data space, same shared memory address space. But these are the obtained summations are written into the local address spaces which is not visible by the address space of processor 0. They are physically different units most likely. So they have to send this value, they have to send this message, they have to pass this message to share the values. Therefore, there is a requirement of data transfer across the network cables here, and that is the essential component and most and the unique demarcating component of distributed memory programming compared to shared memory programming. So message passing can be done like all the processors must be connected via network cable, and they should be able to send and receive data in between each other. This has to be both way, one sends data, other receives it. The other can send data and it can receive it. The advantage is that this is scalable and flexible. You can send data across these two processors while none of they are unaware of this. So you don't need to interrupt the working of the other processor. It has a lot of flexibility. You can send, you can identify which processor gets data, which data it gets from which of the processor, etc., without disturbing other. It's a very flexible system, and it is scalable. You can add as many processors as possible depending on your network. Basically, you have to spend more for the network cable and send data across the processors. Of course, data transfer has its own overhead, but you can do that. It's, nobody can. I mean, there is no hardware restriction for doing that. The cons is, one is that programming is in general more difficult compared to shared memory, because you have to identify the instances for data transfer and send the right data which has to be mapped to the processor. The programming is in general more difficult. Programmer has to ensure data transfer steps through communication across the processors, and also there is another cons that data transfer has its own overhead. So that will add up to certain latency which is more than shared memory programming. So this is called a point-to-point communication in message passing, where each of the points or each of the nodes or processors can share data to any of the nodes in between one point to another point. There is another mode of data transfer here, which is a collective communication, where one processor can send data to all others. It's like one person with standing with a mic and speaking, so everybody gets the information. So this is also possible. There are in message passing paradigm that you can one processor can send data to all other processors, or one processor can get data from all other processors. Like in the previous example, the 0th processor needs to get data from all other processors, processor 1, 2 and 3, which is also possible. Instead of ensuring that it has to one by one interact with all the processors, it can collectively get data from all the processors. That is also possible here. So these are the two, we will discuss about them later, but these are the two main communication, two distinct communication modes in message passing: point to point communication, one by one talks to another, and the collective communication when one gets data or gives data to a group of processors. So the advantage is that universality, message passing model fits well on separate processors connected to by a communication network. Therefore, it matches the highest level of hardware, which is the most fast supercomputer. You can use same message passing model for that. Also, dedicated PC clusters or workstation networks, you have your own PCs, you connect these PCs, is the same message passing protocol which can work over these systems. It is basically it requires different processors which are connected by a network switch, and this communication network can be very fast. You can spend a lot of money and can get very fast 1000 gigabyte per second communication network, or even faster than that. You can use the simple gigabyte per second, 1 gigabyte per second simple internet Ethernet cables, and an 1 gig Ethernet switch for data transfer also. So you can use different, it is very flexible, and you can use different type of network systems. Also, the GPU accelerated computers can be connected, and especially we will discuss about GPU programming, but we will probably not spend time on multi GPU programming. But if you want to ask multiple GPUs to solve a program, GPUs cannot do anything independently. It is the different CPUs which will solve the program. Each CPU is mapped, each CPU is connected with a GPU, and you have to use, you can use something like a message passing model across the CPUs, so that they break the problem into two. If you are using multiple 4 CPUs, say 4 GPUs, you can use a message passing model where the job is broken down to 4 CPUs, and each CPU offloads part of the job assigned to it to the connected GPUs. So multi GPU benefit can also be taken using message passing systems. Expressivity, it is a useful and complete model to express parallel algorithm. It provides the very good control over the programming. The programmer can control many aspects of the program which is missing in database or compiler based models, data parallel or compiler based models like OpenMP. It gives you good data locality and more expressivity. Programmer can express himself more. Programmer can do more, I mean, be more innovative with the parallel algorithms, and do a lot of things more, has more control over the program. Ease of debugging, because it is using local memory and not all the processors not trying to overwrite over a single memory space. The debugging becomes simple. When you have written the program, you can look into one particular processor's behavior and probably find out what are the bugs in the program. And this is very important. Performance is usually better here, because in modern CPUs, the management of memory and cache and memory hierarchy are very important issues to get the right performance. When you use OpenMP or shared memory based parallelization, cache coherence kills this. You have very fast cache, but in order to establish cache coherence, that the advantage of the cutting edge CPU advantage of using a cutting edge CPU is gone, because the first cache speed is killed down by the cache coherence in a shared memory system. However, because you do not need to worry about cache coherence and false sharing in distributed memory system, you can get the benefit of using high performance computers, using the cutting edge computers here. And you are explicitly associating the specific data with the process. You do not need to worry about the other processors work, and therefore the compiler and cache management hardware can function fully. So there are certain advantages over shared memory programming, distributed programming, and these advantages are very obvious. These advantages are very obvious when you are trying to solve a large problem. When you are trying to solve a very large problem with, say, millions of floating point operations to be done in the problem over a large data set, these advantages have become very obvious. So shared memory can be good for working on relatively smaller problems. It is very simple to operate on, and it has less overheads, etc. But distributed memory models are the right thing to do for work on a large problem. So, now we come to message passing interface or MPI. As we said that all the different components of distributed memory programming model will be taken care of MPI. So, we will see what is MPI. MPI is message passing library specification, it is called message passing interface, and this is a message passing model. So, you should write the full name of MPI is message passing interface. It is a message passing model, it is a library that specifies the names, calling sequences and results of subroutines to be called from the Fortran or C program or functions of C programs. So, in a Fortran it is like a subroutine and in C it is a function, MPI works like that, but they are basically library calls. It is not a compiler specification, so it is not a language, it is a library basically. The program that uses the programs that users write in Fortran or C can be compiled with ordinary compilers and compiled with MPI library to get the benefit of MPI. It is not a specific product, there are multiple versions of MPI and multiple releases of MPI from different forums. In short, MPI or message passing interface, it's a message passing application programmer interface together with protocol and semantic specification for how its features must behave in any implementation. So, these are library calls which is written over standard C, C++ or Fortran program, or in a sense many other languages also support MPI, by which you can ensure that the essential elements of distributed memory parallel programming can be taken care of. This is specially designed for message passing across different processors. Again, this is something, it is an API, so it is something similar to OpenMP. OpenMP worked for shared memory system, MPI will work for distributed memory system. These are designed for parallel computers, clusters and heterogeneous networks. In 1993, groups based on parallel computing vendors, software writers and application scientists, they collaborated and developed a standard portable message passing library definitions called MPI for message passing interface. MPI is a specification for library of routines to be called from C and Fortran programs for message passing across different processors. These forums again reconvened in 1995 to 97 and extend MPI to remote memory operations, parallel input-output, dynamic process managements and number of other features which we many times use for writing robust programs in MPI using MPI, and this version is named MPI 2. And when MPI is developed, it was dedicatedly developed for distributed memory systems, but later people found out that adding some shared memory, adapting it for shared memory applications will be very helpful. So, MPI 3, which is released in 2012, adapted shared memory programming too. So, in a sense, the MPI is or message passing interface is a library by which, it is a library specification by which you can make different computers talk to each other, communicate across each other through message passing in a distributed memory system. However, there are certain developments later in MPI which enables it to work it on this shared memory system also. Again, in this particular course, we will look into distributed memory applications of MPI only, which was the main driving factor of development of MPI. The basic functions of MPI, well, say MPI is small and exclusive. That means, like, if you know only few MPI functions, you can take any program and make it parallel. And these MPI functions are these 6 functions: MPI init, which initializes MPI environment; MPI finalize, which exits MPI, which says that MPI environment is over and processors can do something else; MPI comsize, which determines the number of processors within a communicator. We will discuss about communicator later. So, what is COM? COM is communicator. I will probably write it down. This is This is communicator. MPI com rank, which determines the rank of the process within the communicator. MPI send, which sends the message. MPI receive, which receives the message. With these 6 function calls, any program can be parallelized in distributed memory system. So we call it a small and exclusive library system, that with only a small set of functions you can work with MPI. However, MPI is large too. So these are the message passing calls. MPI send is for sending the message, MPI receive is for receiving the message. These are the main message passing calls. MPI is large too, that means a large number of functions or features are available in MPI, useful for various libraries or functions. For though these are sufficient, but you have a large number of features in MPI and different functions in MPI which you can use for more optimized programming. Now, communicator is very important part of MPI, that is the groups of all the processors which will work in a distributed memory system. In shared memory system it is easy, all the processors connected with the RAM share the same memory space and therefore they are part of the shared memory system. And also you can define the number of threads, so few of the threads will be identified and they will work. But in distributed memory system, physically this is difficult. There are multiple processors with their own RAMs and they are connected through a network switch. Now, when you are running a program, you have to identify few of the processors and they are part of the part of this particular MPI program. In shared memory, it was easy in that sense that there is always a processor 0 which gives some of the jobs to the other, launches other thread. There is always a thread 0. When other threads are launched, it asks other threads to work for it. In MPI, though, there will be some processor named processor 0, but in a sense there is no master. It is MPI's job to identify few processors, which is not MPI's job, which is first done by the scheduler, which is scheduling the program. Then when scheduler allocates the resource, MPI knows that this resource is allocated to it, so it groups these processors and tells them that you are working for the same problem, you are working to execute the same executable, and you need to communicate across among them using the MPI calls, and this group is called a communicator. So if we consider programming running in 5 processors, then every process is connected in all the the program is running in 5 processes. Then all these processes must be connected so that they can do point-to-point communication and collective communication, and they can communicate inside them within this communicator. The default communicator is called MPI com world. When you identify that these processes are connected and they can communicate across themselves, the program identifies this group of processes as MPI com world. So if you write MPI com world, it will identify that these processes are involved in running the program. So whatever I am writing, it should be within these processes. Physically, it is the computers which are connected via the network cable, or the CPUs which are connected via the network cable and communicating across themselves. If there is no network cable, you are doing multi-threading, or you are using a SMP machine to work in the distributed memory systems, these processors which are executing that particular program, it is always a single program, multiple data model, which are executing the program, the processors which are responsible for executing the program, they are grouped, and this group is called the communicator. So when they have to communicate within the group, that means via the communicator. MPI com world is the default name of the communicator, so all of the MPI calls which requires access or which requires coordination among multiple processors must mention that they are working on through the communicator MPI com world. So if there are 5 processors working in between them, all of them can share data in between them each other, they can do a point-to-point share, and they are connected in that way. There is a network cable, however, virtually for the program they are connected directly in between each other, and this connection group, this group of all the processors and their connection is called the communicator MPI COM world. This is the elementary block of the parallel program, that any data message passing, any data transfer works within this group or within MPI COM world. So, when a parallel program is launched, the processors are identified, connections are established in between them so that they can do point to point data transfer as well as collective data transfer, and this group, that these processors are executing this program through MPI and they are doing data transfer through MPI across themselves with all the flexibilities. Any processor can send data to any other processor. The entire group is identified by as MPI COM world. This is the default communicator. You can get derived communicator also, communicator within a communicator, which we are not discussing here. But any MPI call which requires synchronization or communication across the processor must mention MPI COM world, so that it identifies that in the whole network these processors and their connectivity is being taken care of through this call. Consider these 5 processes running. MPI COM world will represent the connected group. If processor 0, 1, 2, 3, 4, these 5 0, 1, 2, 3, 4, these 5 processes are running, the MPI COM world will identify their group and the connections. The connected group will be identified as MPI COM world. So, it is like when I made this slide in PowerPoint, what I did, I draw these circles, they are the processors. I draw the lines connecting in between them, and then I selected everything, made a right click and grouped them. Now I can move this group as I wish, and this particular group is communicator or MPI COM world. So, what we do in PowerPoint, we get many elements and group them. Similarly, there are many processors, there are connections in between the processors, communications in between the processors, we group them. This group is called the communicator, and the default name of the communicator is MPI COM world. Through this communicator, they can send receive data among each other. We will see its uses later. The number of communicator does not change once it is created. The number in a communicator does not change once it is created. So, once we write MPI init or initialize MPI, it identifies the resource allocated to it and builds a communicator. Once this communicator is built in, the number of processors will not change. In OpenMP, you can remember, you can change the number of threads, but in MPI you cannot change the number of processors. Once the communicator is built, the number of processors are identified and this will remain. The entire program will be executed in these processors. If you do not try to do anything or something, you do not try to run a program, part of the program in one of the processors, you have to do something as a programmer, you have to write some if else statement, etc. However, in general, the entire program will be executed in all the processors assigned to that communicator, and that is once done, it cannot be changed. And the number of processors inside the communicator is called the size of the communicator, and at the same time each processor inside the communicator has a unique number to identify it. We can see 0, 2, 4, each processor has its unique number, and this number is called the rank of the process. Each process has its unique number. I sometimes mention processor in terms of process, but the correct word is process here. Each process has its unique number and this number is identified as the rank. So, 2 important questions arise in a parallel program. How many processes are participating in the computation? That means, what is the size of the communicator, and who am I? What is the identity of the particular process in that? And MPI provides functions to answer the questions. If you write the function MPI COM size, its output is the size of the communicator or the number of processes in the communicator, the size. If you write MPI COM rank, each processor or each process will return a unique ID, which is the ID of that process. If the rank of the processes starts from 0 and ends at size -1, because size is the total number of processes here. So, size and rank are 2 important features here, and many times we have seen in shared memory programming also, many times you need to know about the rank of the process and the size of the size of the computation also. So these will be required as and when many times. So now we come to our first MPI program, which is again same as the first OpenMP program. We are discussing about Hello World program. It starts with, after stdio.h, it starts with #include mpi.h. That means this is the MPI library which has to be included, MPI library header function. And when we write this program, MPI init with an argument, integer argument and character argument as in input of the functions. There are certain things which it writes here. Once we will write the output, we will see it initializes the MPI, then MPI com rank gets the current process ID, MPI com size gets the number of processor, and then it prints hello world from process this and the size of this particular size. It writes the rank and size, and MPI finalizes it, and the return is 0. So this is the MPI header, mpi.h. We can see that when we need to synchronize or coordinate or communicate across many processes, except initialize and finalizing, we have to use MPI com world, which is the communicator which tells that you are working within this group. So what is the size of this group? What is your ID in that particular group? So both com rank and com size as well as send receive, we will see later, requires the communicator, which is in most MPI calls which is present, MPI com world. And these MPI functions return the size and rank. Well, we can compile this with MPI cc hello world .c. MPI cc is the compilation command. So this is a wrapper over the GCC compiler. In GCC it is MPI cc hello world.c. MPI cc, similarly MPI C++ in C++, MPI F77, MPI F19, Fortran 77 and 90 is a program that wraps over an existing compiler to set necessary command line flags when compiling the code which is using MPI. So in OpenMP it was a compiler option, but here it is a program which is the wrapper over the compiler, which is to be called. Typically it adds few flags to enable the code to be compiled and linked against MPI library in C++ and Fortran. And MPI is also supported by other languages like Java, Python, Julia, R, MATLAB. For Julia, MPI works very good. This is another point, but many other languages are also supported using MPI. Well, so if we write this program in Fortran, we have to include mpif.h. For Fortran, the header file is different, mpif.h, and all the functions are now subroutines and they are called, and again with they are not called, the input is not void or some address space, but rather an integer IR. So there is an integer value with error code which will be input of all the functions. If the function if the MPI call is successful, this error code will return an integer value, is non-garbage integer value, usually it is 0. If it is unsuccessful, it will return something garbage. So there is an error code which comes with all the MPI function calls, and these are not function calls, they are subroutine calls because it calls these functions. Well, this is the same hello world program, and instead of just writing the function, is the function call here, and the function call requires an error code IR. That is the difference in Fortran. And it has to be compiled with MPI F77 hello world.f or MPI F90 if it's Fortran 90. This can be compiled. This is Fortran 77, but can also be compiled in Fortran 90. MPI F90 hello world.f. So it is again using another wrapper here. Now the execution is MPI run -np, then number of processors that you want to run and the executable file. Say I want to run it in as 8 processes, so MPI run -np 8 a.out, and the output will be hello world from process with the rank, this is rank and this is size. So each of the process is writing its rank and the size of the processes. If I run it in 4 processes, then 0, 1, 2, 3. Now you can see, though it's written sequentially, but it's not ensured that sequentiality will be maintained. There is no specific order in writing by the processors, because it's different processors which are writing to the screen, and they can do it in their own order. So the order is not maintained when you are writing MPI. Output from MPI is very similar as OpenMP. In OpenMP still you can control it using the ordered construct, but in MPI this synchronization across the processors are not possible, so you cannot make an order. Well, if you simply run the executable, it will run on a single process. If you do not write MPI run minus NP, then this is an integer value of how many processes you want to run, and the executable. If you simply run the executable, this will be running as a sequential code, and it will run in a single process. It can be important to check the environment in which an MPI program is running. So we write a program which will write down the environment. What it will write? That first is that what is the output of MPI init? We say in Fortran MPI init comes with an error code I here. In C it comes with an argument argc and argv. So what is, and the output is rc. What is the rc? It's a function, so there should be some output of the function. What is the output of the function? So this output is an integer, and we will write the integer value. This value is same as the I here in Fortran. Then if this value is not equal to MPI success is assigned to be a value 0. If the output is non-zero, then there is no success. Then it will write that error in starting MPI program. Something is wrong with the libraries or with software or hardware level. If it is, and then it will call MPI abort, that the program will come out of the MPI stage. MPI is not finalized, it's not finished, but the communicator will be destroyed because MPI is not running correctly. If not so, then it will find out the COM size, the COM rank, and MPI get processor name. This MPI abort and MPI get processor name, they are not part of our 6 function calls which are sufficient to write an MPI program. So though MPI is small, but MPI is also large, we can add more function calls in that. I mean, we can use some features which are not those 6 basic calls. Out of that, one of them is MPI abort. Similarly, one is MPI get processor name, which will identify name of the processor which is executing the job and write it, and then you can physically see which computer is executing that program. If you write MPI rank, it will tell you which process within the communicator, which process ID is executing the job. If you use MPI get processor name, so in host name it will be written that which processor is actually executing the job. You will see that the name of the processor, the host name of the processor here, and this will give you help you to check the MPI environment. So once you execute that, it runs in 2 processors. So each process, now you can see each process writes the printf statement is this one. Printf is this is MPI is rc is equal to MPI success. MPI has worked fine, so this will not be written. So printf statement is this one and this one. So each process is executing one of the all the printf statements. So it is MPI call return value rc gives a value 0. The return of MPI init call is 0, and it writes number of tasks 2 is the MPI com size, that is num tasks is 2, the rank is 0 for this processor, and running on the host name which is, it is running on a machine called Alivardi from IIT Kharagpur, alivardi.iitkgp.ac.in. In the same machine, another processor is running in another another processor is running on the, it's a multi-core machine on another processor of the machine. So the second one is also running the same, writing the same name, but it's the same machine which has multiple processors. Different processors are executing different processes, and the rank is here 1. So successful MPI calls will always return the MPI init or any all this has the RC value. If you all these programs can be, functions can be associated with one integer value, and this integer value, if the call is successful, then this integer value is 0. In Fortran, we can probably go back and see Fortran code. In Fortran, this I error is there with all the MPI calls. The what is the output of the function? The same, because Fortran is calling it, is same as the variable I error that the Fortran MPI subroutines are returning in Fortran. So in Fortran, if it is successful, then I error is equal to 0. This gives the same function call. Well, so we in the first basic discussion on how MPI programs are do look like and what are the important features, including communicator. These are the references. Especially William Grubb's book is a canonical text in MPI, and you can look into Lawrence Livermore National Labs website to get MPI tutorials. We will discuss some of the problems. We have discussed about distributed memory programming model, message passing interface, and MPI is discussed, and basic MPI programs and hello world program is shown. Based on that, we will work on the send receive operations in MPI in the subsequent classes. Thank you.